Tonight, as you drift towards sleep, we will explore why leaving the Milky Way is beyond current physics and engineering. Clear facts about distance, energy, and time show practical limits that ease the mind. Rest while learning why, for now, our home galaxy is where human journeys stay. Tonight, we are not going to talk about conquering the stars or building fleets that sail between alien suns. Instead, we are going to settle into something quieter, something perhaps a little humbling, and ask a question that has no easy answer and no comforting escape. Why will we, as a species, as a civilization, as tiny architects of metal and dream, never leave our galaxy? Not in 1,000 years, not in 1,000,000, and likely not ever. This is not a story of failure or defeat. It is not pessimism dressed up in science. It is simply the truth written in the fabric of space itself, in the laws that govern light and distance and time. And it is a truth worth sitting with, slowly, because in understanding the edges of what is possible, we also come to understand something profound about our place in this vast, silent universe. Before we begin, I would love to know where you are right now. Are you lying in bed, the room dark except for the faint glow of a screen? Are you listening as the world outside quiets down, as the day releases its grip on you? Wherever you are, whatever time it is, I am glad you are here. If this kind of question, this slow unraveling of cosmic limits, is something that speaks to you, I would be grateful if you tapped like or subscribed. It helps this quiet signal reach others who wonder about these things, who look up at the night sky and feel both wonder and a strange, aching smallness. But there is no pressure, only an invitation to share this moment, this journey through the dark. So settle in. Let your mind drift outward, past the ceiling, past the clouds, past the thin envelope of air that keeps us alive, and into the black. We are going to travel far tonight, farther than any human has ever gone, and then we are going to confront the wall that stands between us and everything beyond. It is not a wall made of stone or metal. It is a wall made of distance, of physics, of time itself, and it is absolute. When we look up at the night sky, we see stars, thousands of them, scattered like salt across black velvet. They seem close, almost within reach, as if we could climb high enough or sail far enough to touch them. But that closeness is an illusion, a trick of perspective played on minds that evolved to understand the distance between trees, not the distance between suns. The truth is that every point of light you see, every star that twinkles in the dark, is so far away that the numbers lose meaning. The nearest star to our sun, Proxima Centauri, sits just over 4 light-years away. That means the light we see from it tonight left that star 4 years ago, travelling at the fastest speed the universe allows, and it is only just now arriving at your eyes. 4 years of travel at the speed of light, and that is the closest star. Most of the others you can see are tens, hundreds, even thousands of light-years away, and all of them, every single one, belong to our galaxy. Our galaxy, the Milky Way, is a vast spiral of stars, gas, dust, and darkness. It stretches roughly 100,000 light-years from edge to edge, a disk of light spinning slowly in the void. Within it, there are somewhere between 200 and 400 billion stars, each one a sun, many of them with planets, some of those planets perhaps carrying life. It is almost incomprehensibly large, a city of suns so immense that light itself, the fastest thing there is, takes 100,000 years to cross from one side to the other. And yet, for all its size, the Milky Way is just one galaxy among billions. Some estimates suggest there are 2 trillion galaxies in the observable universe, each one an island of stars, each one separated from the others by distances that make the width of our own galaxy seem like a short walk. The nearest large galaxy to ours is Andromeda, a spiral much like the Milky Way, home to perhaps 1 trillion stars. It is so large that if you could see it fully with the naked eye, it would stretch across the sky 6 times wider than the full moon. But it is far, unimaginably far. Andromeda lies about 2.5 million light-years away. That means the light we see from it tonight began its journey 2.5 million years ago, long before humans existed, long before our ancestors walked upright on the plains of Africa, light that left Andromeda when the Earth was in the grip of the Pliocene epoch, when saber-toothed cats and giant ground sloths roamed the continents, has only just arrived here now as you listen to these words. And Andromeda, for all its distance, is our closest neighbour. Beyond Andromeda, the distances grow even more staggering. The Triangulum Galaxy sits 3 million light-years away. The galaxies of the Virgo cluster, a collection of over 1,000 galaxies, lie roughly 50 to 60 million light-years distant. And farther still, galaxies we can barely resolve with our most powerful telescopes sit billions of light years away, their light so old that it shows us the universe as it was when stars and galaxies were still young, still forming, still learning how to shine. These are the distances we are speaking of when we talk about leaving our galaxy. Not the distance to the moon, which humans crossed in 3 days. Not the distance to Mars, which our robots have reached in months. We are talking about distances so large that they break the human mind. Distances that make a mockery of our ambitions and our dreams of spreading across the stars. But perhaps you are thinking, surely with enough time, with enough advancement, we could do it. Surely, if we build the right ships, develop the right technologies, wait long enough for science to catch up with imagination, we could cross that gap. After all, we have done impossible things before. We have split the atom, walked on the moon, sent machines to the edge of the solar system. Why not this? Why not the leap to another galaxy? The answer lies not in our creativity or our will, but in the structure of reality itself. It lies in the speed of light, in the nature of space and time, in the simple, unbreakable rules that govern how the universe works. These are not challenges to be overcome with better engineering or smarter designs. They are limits, hard limits, written into the very code of existence. And to understand them, we need to start with the one thing that defines all cosmic travel, the one barrier that cannot be crossed or negotiated or bypassed. We need to understand light. Light moves fast, faster than anything else in the universe. In the emptiness of space, light travels at roughly 299,792,458 meters per second. We usually round it to 300 million meters per second, or about 186,000 miles per second, because the precision hardly matters at this scale. What matters is that this speed is absolute. It is the speed limit of the cosmos, the maximum velocity at which anything, any particle, any wave, any piece of information can move through space. Nothing with mass can reach the speed of light. Nothing can exceed it. And this is not a technological limitation. It is not something we might one day overcome with a clever innovation or a bold experiment. It is a law as fundamental as the existence of space and time themselves. Einstein showed us this in his theory of special relativity, and every experiment, every observation, every test we have conducted since has confirmed it. The speed of light is the ceiling, and we are bound beneath it. Now at first, 300 million meters per second sounds fast enough for anything. After all, at that speed, you could circle the Earth more than 7 times in a single second. You could travel from the Earth to the Moon in just over a second. You could reach the Sun in about 8 minutes. Surely, with speed like that, no distance is too great. But space is not measured in kilometers, or even millions of kilometers. Space, especially the space between galaxies, is measured in light years, and light years swallow speed whole. A light year is the distance light travels in 1 year, moving at 300 million meters per second, never slowing, never stopping. Light covers roughly 9.5 trillion kilometers in that time. That is the unit we use to measure the cosmos, and it is the unit that reveals just how trapped we are. To reach Andromeda, our nearest galactic neighbor, light takes 2.5 million years. That is not 2.5 million years of slow travel. That is 2.5 million years moving at the fastest possible speed in the universe. There is no faster way to go. If we somehow built a ship that could travel at the speed of light, which we cannot, it would still take 2.5 million years to reach Andromeda. The crew that departed Earth would not live to see the destination. Their children would not live to see it, nor their children's children, nor 100,000 generations after them. By the time the ship arrived, if it ever did, humanity as we know it might not even exist anymore. Our languages would be forgotten, our civilizations would be dust, the very continents on Earth would have shifted, the climate would have changed, and evolution itself would have had time to reshape the living world. 2.5 million years is not a journey. It is an exile into deep time, a one-way voyage into a future so distant that the word future loses all meaning. And that is assuming we could travel at the speed of light, which we cannot. No object with mass can reach that speed. As you accelerate closer and closer to the speed of light, strange things happen. Your mass increases. The energy required to push you faster grows exponentially. By the time you approach 99% of light speed, you would need more energy than exists in entire solar systems just to nudge yourself a fraction of a percent faster. At 99.9%, the energy requirements become absurd, exceeding the output of stars. And even if you somehow found that energy, even if you could reach 99.99% of the speed of light, you would still be moving slower than light itself, and the journey to Andromeda would still take millions of years. There is no loophole here, no clever trick, no hack hidden in the equations. The universe simply does not allow it. But let us imagine, just for a moment, that we could. Let us imagine that we built a ship capable of traveling at, say, 10% the speed of light. This is wildly optimistic, far beyond anything we can currently do, but let us grant it for the sake of the thought. At 10% of light speed, the ship would be moving at 30,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in about 13 seconds, fast enough to reach the Sun in less than an hour and a half. It sounds miraculous, and by every human measure it would be, but in the context of intergalactic space, it is heartbreakingly slow. At 10% of light speed, the journey to Andromeda would take 25 million years, not generations, not centuries. 25 million years, longer than the entire history of the genus Homo, longer than most mammal species exist before going extinct. It is not a journey any human could take, or any civilization could plan for, or any species could survive. Andromeda is the closest galaxy. Most galaxies are far, far farther. The distances stretch into the hundreds of millions, the billions of light years. To reach them, even at a significant fraction of light speed, would require time spans that exceed the current age of the universe. You would set out on a journey that could not be completed before the stars themselves began to die, before galaxies aged and faded, before the universe grew cold and dark. You would be sailing not toward a destination, but toward oblivion, moving through a void so vast that arrival is not a question of when, but whether the universe itself will last long enough for it to happen. This is the first and most fundamental reason we will never leave our galaxy. Distance. Not distance as we understand it in our daily lives, but distance on a cosmic scale. Distance that turns time into geology, that turns journeys into epochs. We are islands, isolated by an ocean of space so wide that even light, the fastest traveller in existence, cannot cross it within the span of a human life, or a human civilization, or even a human species. And speed, the tool we have always used to conquer distance, is no longer enough. We have reached the edge of what speed can do, and we have found that the universe is simply too large for us to overcome it by going fast. But this is only the beginning. Distance and speed are just the first wall. There are others, each one higher, each one more impassable. There is the question of energy, of what it would take to push even a small ship to a meaningful fraction of light speed. There is the question of time, of what happens to those who travel at such speeds, of how the universe itself changes around them. There is the question of resources, of whether it is even possible to carry enough fuel, enough material, enough life support to sustain a journey measured in millennia or longer. And there is the question of what lies between the galaxies, the great voids, empty and silent and darker than anything we have ever known, spaces where there is nothing to find, nothing to use, nothing to navigate by. Each of these questions leads to the same conclusion that the space between galaxies is not just far, but fundamentally unreachable, a boundary we are not meant to cross. And so we will explore them, one by one, gently, without hurry. We will look at the energy required to move through space, at the fuel needed to accelerate a ship to even a fraction of light speed, and we will find that the numbers are staggering, impossible even. We will look at time, at how it bends and stretches for those who travel fast, and we will find that the faster you go, the stranger the universe becomes until you are no longer traveling through space, but through time itself, watching the universe age around you while you remain untouched. We will look at the voids, the empty expanses between galaxies, and we will find that they are not like the space between stars, not dark, but rich with hidden matter and light. They are true voids, empty in a way that is difficult to grasp, places where even the faint glow of distant galaxies fades into nothingness, leaving only black. If distance is the first wall that traps us within our galaxy, then energy is the second, and it is just as unforgiving. To understand why we will never leave the Milky Way, we must confront not only how far we would need to travel, but what it would take to actually move through that distance. And the answer, when we calculate it carefully, when we look at the raw numbers and the physics behind them, is so overwhelming that it borders on the absurd. It is not that we lack the will or the vision to build ships capable of intergalactic travel. It is that the universe itself demands a price we cannot pay, an energy cost so high that it might as well be infinite. Let us start small with something we can understand. Imagine you want to throw a ball. You pull your arm back, you put energy into the motion, and you release. The ball flies through the air, fast at first, then slower as gravity and air resistance pull at it until it arcs down and stops. Simple. The energy you used came from your muscles, which got it from the food you ate, which got it from the sun by way of plants or animals. A clear line of energy from star to ball, with you as the intermediary. Now imagine you want to throw that ball faster. You need more energy. You wind up harder. You push more force into the motion. If you want the ball to go twice as fast, you need not twice the energy, but 4 times, because kinetic energy, the energy of motion, scales with the square of velocity. Twice as fast means 4 times the energy. 3 times as fast means 9 times the energy. 10 times as fast means 100 times the energy. This is not intuition, this is mathematics, and it does not negotiate. Now scale this up. Instead of a ball, imagine a spacecraft. Instead of throwing it across a field, imagine accelerating it to a speed sufficient to travel between stars or between galaxies. The energy required does not just increase, it explodes. Let us put some numbers to this, not because numbers are comforting, but because they make the impossibility clear. Suppose we want to send a spacecraft to Andromeda. Suppose this spacecraft weighs about 1,000 kilograms, roughly the mass of a small car. Not a large ship, not a vessel capable of carrying a crew or supplies for a long journey, just a tiny probe, a machine with instruments and perhaps a message. 1,000 kilograms, a specification. To accelerate this probe to 10% of the speed of light, which as we discussed would still take 25 million years to reach Andromeda, we would need to give it a kinetic energy of roughly 4.5 times 10 to the power of 17 joules. That is 450 quadrillion joules, or about 125 trillion watt-hours. To put that in perspective, that is several times the total annual energy consumption of the entire human species. Every power plant, every engine, every battery, every bit of energy we generate in a year, all of it, would not be enough to accelerate a single tiny probe to just 10% of light speed. But let us continue. Suppose we wanted to go faster, say 50% of the speed of light, to cut the travel time down to a merely absurd 5 million years. Now the energy required jumps to roughly 1.1 times 10 to the power of 19 joules. That is 11 quintillion joules. Thousands of years of humanity's total energy output just to move one small probe. And if we wanted to reach something closer to the speed of light itself, say 90%, the energy requirements become even more grotesque, swelling into numbers that dwarf the total energy output of our sun over long periods. At some point, the numbers stop meaning anything. They become abstract, symbols on a page, because there is no human-scale comparison that makes sense. We are talking about energy on the scale of stars, of supernovas, of cosmic events so violent that they reshape galaxies, and this is just to move a probe the size of a car. Now imagine trying to move something capable of sustaining human life. A ship that could carry people, food, water, air, waste recycling systems, shielding against radiation, redundant systems in case of failure, all the infrastructure needed to keep a crew alive for years, decades, or longer. Such a ship would weigh not 1,000 kilograms, but millions, possibly tens or hundreds of millions of kilograms. The energy required to accelerate such a ship to even a modest fraction of light speed would exceed the total energy humanity has generated in its entire history. And we have not even talked about fuel yet. Because here is the problem. Energy does not just appear, it has to come from somewhere. In space, there are no gas stations. There is no place to refuel, no convenient stop where you can top off the tanks and continue on your journey. Any energy your ship uses has to be carried with it, stored somehow in fuel or batteries or some other form, and fuel has mass. If your ship needs energy to accelerate, it needs to carry fuel. But the more fuel it carries, the heavier it becomes, and the heavier it is, the more energy it needs to accelerate. This is the tyranny of the rocket equation, a mathematical law that has governed every spacecraft ever built, and it is merciless. Every additional kilogram of fuel you add makes the ship heavier, which means you need even more fuel to reach the same speed, which makes it heavier still, which means you need even more fuel, on and on in a vicious spiral. At a certain point, the mass of the fuel required becomes so enormous that it exceeds any reasonable limit. You end up with a ship that is 99.9% fuel and almost nothing else, and even then, it cannot carry enough to reach the speeds necessary for intergalactic travel. Let us consider an example. Chemical rockets, the kind we use to launch satellites and send probes to other planets, are incredibly inefficient when it comes to deep space travel. They work by burning fuel and expelling the exhaust at high speed, using Newton's third law to push the rocket forward. But the exhaust velocity, the speed at which the fuel is thrown out the back, is limited by chemistry. For the best chemical rockets, exhaust velocities are around 4 to 5 kilometers per second. To reach even a tiny fraction of the speed of light using chemical propulsion would require so much fuel that the mass ratio, the ratio of the fuel to the payload, would be astronomically high. We are talking about ratios of millions or billions to one. You would need to carry billions of kilograms of fuel for every kilogram of payload. It is simply not feasible. The rocket would collapse under its own weight before it ever left the ground, so chemical rockets are out. What about nuclear propulsion? Nuclear reactions release far more energy than chemical ones. A nuclear rocket, one that heats a propellant using a nuclear reactor and expels it out the back, could achieve exhaust velocities of perhaps 10 to 20 kilometers per second. Better, but still nowhere near enough. Even with nuclear propulsion, reaching 10% of the speed of light would require fuel mass ratios in the thousands. You would need a ship the size of a mountain to carry enough fuel to accelerate a tiny payload to a meaningful speed. And nuclear fission, while powerful, is still limited by the amount of energy that can be extracted from splitting heavy atoms. Fission is not enough. The energy density is too low. What about nuclear fusion? Fusion, the process that powers the stars, releases even more energy than fission by fusing light atoms together. A fusion rocket could, in theory, achieve exhaust velocities of hundreds or even thousands of kilometers per second. This is starting to get interesting. With fusion, the fuel mass ratios drop into a more reasonable range, though still challenging. You might need a ship that is 90% fuel by mass, but at least it is within the realm of imagination. If we could master controlled fusion, and that is a significant if, we might be able to build a ship capable of reaching a few percent of the speed of light. Not enough to make intergalactic travel practical, but enough to explore the nearer stars within our galaxy, assuming we were willing to accept journey times of centuries or millennia. But even fusion has its limits. The problem is that fusion fuel, isotopes like deuterium or helium-3, still has mass. You still have to carry it with you, and you still hit the rocket equation. And to reach the kinds of speeds necessary for intergalactic travel, even fusion is not enough. You would need something far more powerful, something that converts mass directly into energy with perfect efficiency. You would need antimatter. Antimatter is the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate each other completely, converting their entire mass into energy, according to Einstein's famous equation, E equals mc squared. The energy released is staggering. A single gram of antimatter, annihilated with a gram of matter, releases the energy equivalent of a small nuclear bomb, roughly 43 kilotons. If you could carry antimatter as fuel and use it in a rocket, you could achieve exhaust velocities approaching the speed of light. The fuel mass ratios would finally be reasonable. You could, in principle, build a ship capable of reaching a significant fraction of light speed without needing to be the size of a planet. This is the dream of the antimatter rocket, and it is not entirely science fiction. The physics works, at least on paper. But there is a catch, and it is a big one. Antimatter does not exist naturally in any useful quantity. It has to be made, and making it requires energy, enormous amounts of energy. To create a single gram of antimatter using current technology would require roughly 100 trillion watt-hours of energy, far more than the total annual energy production of most countries, and that is assuming perfect efficiency, which we cannot achieve. In practice, the energy cost is even higher. Antimatter is also fantastically difficult to store. It cannot touch normal matter, or it annihilates instantly. It has to be contained using magnetic fields in a perfect vacuum, and even then it is unstable and prone to loss. The infrastructure required to produce and store enough antimatter to fuel an intergalactic voyage would be beyond anything humanity has ever built. We are talking about energy investments on the scale of entire civilizations over centuries just to create the fuel for a single journey, and that is before we even build the ship. So even with antimatter, the most powerful fuel the laws of physics allow, the energy costs of intergalactic travel remain prohibitive. Yes, it might be theoretically possible to build a ship that could reach 10 or 20% of the speed of light, but the energy required to do so, the resources, the time, the industrial capacity, all of it is so far beyond what we can currently imagine that it might as well be magic. And even if we did it, even if we spent centuries building the infrastructure, producing the antimatter, constructing the ship, we would still only be traveling at a fraction of light speed, and the journey to Andromeda would still take millions of years. The energy barrier is not something we can engineer our way around. It is fundamental, a consequence of the relationship between mass, velocity, and energy. The faster you want to go, the more energy you need, and at the speeds required for intergalactic travel, the energy demands become so great that they exceed the resources available to us, perhaps to any civilization. There is another dimension to the problem of intergalactic travel, one that emerges not from the engines we might build or the fuel we might carry, but from the nature of time itself. This is where physics stops feeling like engineering and starts feeling like philosophy, where the journey becomes not just a question of how far or how fast, but of what it means to travel at all. Because when you move through space at speeds approaching the speed of light, time does something strange. It bends, it stretches, it becomes relative, slipping and sliding in ways that defy common sense. And this transformation of time, predicted by Einstein and confirmed by every experiment we have run, adds yet another layer to the impossibility of leaving our galaxy. Even if we solved the energy problem, even if we built the perfect ship and fueled it with antimatter, we would still have to reckon with the fact that the universe does not experience time the way we do, and at high speeds, the difference becomes profound. This is the phenomenon known as time dilation, and it sits at the heart of Einstein's theory of special relativity. The basic idea is simple, though its implications are dizzying. Time is not absolute. It does not flow at the same rate for everyone. Instead, the rate at which time passes depends on how fast you are moving relative to something else. If you are standing still, time passes normally. But if you start moving, especially if you move very fast, time slows down for you relative to someone who is not moving. The faster you go, the more pronounced the effect becomes. And at speeds close to the speed of light, time dilation becomes extreme. Let us make this concrete. Imagine you board a spacecraft capable of traveling at 90% of the speed of light. You leave Earth and head toward a distant star, let us say one that is 10 light years away. From the perspective of someone on Earth, the journey takes just over 11 years. You are moving at 90% of light speed, so the distance of 10 light years is covered in roughly 11 years of Earth time. Simple. But from your perspective, aboard the ship, time passes differently. Because you are moving so fast, time has slowed down for you. Clocks on the ship tick more slowly. Your heartbeat, your thoughts, the decay of particles in your fuel, everything happens at a slower rate compared to the clocks on Earth. For you, the journey does not take 11 years. It takes only about 4.5 years. You experience less time. The journey feels shorter. You arrive at your destination, and when you check the calendar, only 4.5 years have passed for you. But when you radio back to Earth, you learn that 11 years have passed there. This is not an illusion or a trick. Both perspectives are correct. Time genuinely passed more slowly for you because you were moving fast. Now imagine you push the speed even higher. Suppose your ship travels at 99% of the speed of light. Now the time dilation effect is much stronger. A journey that takes 100 years of Earth time might take only about 14 years for you. At 99.9% of light speed, 100 years of Earth time compresses to about 4.5 years for you. 99.99%, it drops to just over 1 year. The closer you get to the speed of light, the more extreme the effect becomes. At speeds infinitesimally close to light speed, you could, in principle, travel vast distances while experiencing only days, hours, or even minutes of subjective time, even though thousands or millions of years pass in the outside universe. This sounds like a cheat code, a way to bypass the vast distances of space. If you can compress subjective time so drastically, then maybe intergalactic travel becomes possible. You could board a ship, accelerate to near light speed, and arrive at Andromeda in what feels feels like a few decades, or a few years, or even less, depending on how close you get to light speed. For you, the traveler, the journey would be survivable, even reasonable. You would age normally. You would live a normal life aboard the ship. And when you arrived, you would step out into a distant galaxy, having crossed 2.5 million light years of space. But here is the problem. While the journey might feel short for you, the universe does not stop. For everyone and everything you left behind, time continues at its normal pace. If you travel to Andromeda at near light speed and the journey takes you, say, 30 years of subjective time, you arrive to find that 2.5 million years have passed on Earth. Everyone you knew is gone, not just dead but erased by time. Your entire civilization, every trace of the world you left, is almost certainly gone. Humanity, if it still exists, will have evolved into something unrecognizable. Languages will have changed beyond comprehension. Entire epochs of history will have unfolded. Continents will have drifted. Species will have risen and fallen. The Earth you return to, if you ever return, will be as alien to you as any distant planet. And there is no way to avoid this. Time dilation is not optional. It is not something you can turn off or mitigate. If you travel fast, time slows for you, and the outside universe ages. This creates a fundamental asymmetry. You can, in theory, travel vast distances in a subjective human lifetime, but you cannot bring anyone with you in any meaningful sense. You cannot maintain a connection to the place you came from. You are not traveling through space. You are traveling through time, leaping forward into the deep future with every light year you cover. You become a time traveler, exiled from your own era, severed from the stream of history. This is not a journey, it is a disappearance. For intergalactic travel, the implications are crushing. Even if we built a ship capable of reaching Andromeda in a reasonable subjective time, the mission would be one way in every sense that matters. The crew would leave Earth knowing they could never return to the world they knew. They would arrive in Andromeda to find that any signals, any communications, any updates from home had stopped millions of years ago. They would be utterly alone, not just in space, but in time. And if their mission was to explore Andromeda and report back, the report would arrive on Earth millions of years after the civilization that sent them had vanished. The data, the discoveries, the entire purpose of the journey would be received by no one, or by beings so different from us that they might not even recognize it as meaningful. This temporal isolation makes intergalactic travel not just impractical, but pointless. What is the purpose of sending a mission if the results cannot return in time to matter? What is the point of exploration if the explorers are severed from everything they explore for? We might say that the purpose is knowledge, that the value lies in the act of discovery itself, that the crew carries the meaning with them. And perhaps that is true in some abstract sense, but practically, psychologically, it is a barrier as insurmountable as distance or energy. Who would volunteer for such a journey? Who would agree to leave behind not just their home but their entire timeline, to step into a future where nothing they knew remains? It is a form of existential exile that is difficult to comprehend, and it is built into the physics of high-speed travel. There is also the question of what you would see along the way. Time dilation does not just affect clocks and aging, it affects your perception of the universe. As you accelerate toward the speed of light, the light from stars in front of you becomes blue-shifted, compressed in wavelength, while the light from stars behind you becomes red-shifted, stretched. The sky distorts. Stars in front of you appear to cluster together, growing brighter and bluer, while stars behind you fade into red and dim. At extreme speeds, the universe ahead of you would look like a bright ring of compressed light, while the universe behind you would sink into darkness. You would be traveling through a distorted, warped version of reality, a space where even the familiar stars no longer look like themselves. And there is another effect, more subtle, but no less strange. As you move at relativistic speeds, the universe itself appears to change. Distances in the direction of your travel contract, a phenomenon called length contraction. A galaxy that is 2.5 million light-years away when you are at rest appears shorter when you are moving toward it at near light speed. From your perspective, the distance compresses, which is part of why the journey feels shorter. But this is not just perception. It is a real feature of how space and time are woven together. Space and time are not separate. They are part of a single fabric, space-time, and your motion through that fabric determines how you experience both distance and duration. The faster you move through space, the less you move through time, and vice versa. Everything is connected, and the trade-offs are built into the structure of reality. But even setting aside the philosophical and psychological difficulties, time dilation introduces practical problems. Suppose you are part of a mission to explore Andromeda, and you plan to send back information, updates, reports on what you find. Every signal you send back to Earth travels at the speed of light. If you are halfway to Andromeda, 1.25 million light-years from Earth, any message you send will take 1.25 million years to arrive. By the time it gets there, the people who sent you are long gone. The entire history of the mission, from launch to arrival, unfolds in a time frame so long that no continuity is possible. There is no mission control to guide you, no support, no ability to course correct or call for help. You are not just isolated in space, you are isolated in time, adrift in a future that has no memory of you. And if you think about multiple ships or a series of missions, the problem only multiplies. Imagine we send one ship to Andromeda, and then 1,000 years later, we send another with better technology. That second ship might arrive before the first one because technology has improved and it travels faster. The timeline becomes tangled. Ships pass each other in the dark, separated by millions of years of Earth time, but occupying the same slice of space-time. There is no coherent narrative, no shared history, just a scattering of missions that exist in parallel timelines, unable to communicate, unable to coordinate. The very idea of a sustained effort to explore or colonize another galaxy falls apart when confronted with the realities of time dilation. This is not a problem we can engineer around. We cannot build a clock that ticks at the same rate for everyone. We cannot anchor time to some universal standard and force it to behave. Time is relative, and that relativity is woven into the structure of the universe at the deepest level. It is as fundamental as the speed of light, and just as unyielding. So even if we could build the ships, even if we could find the energy, even if we could survive the journey, we would still be fighting time itself. And time, it turns out, does not care about our ambitions. Even if we somehow found a way to generate the energy, even if we built the ships and resigned ourselves to the strange effects of time dilation, there is yet another obstacle, one less about the laws of physics and more about simple survival. Space is not empty. It is not a calm, still void waiting patiently for us to cross it. Space is hostile in ways that are difficult to overstate, filled with invisible hazards that pose existential threats to anything trying to move through it at high speed. And the faster you go, the more dangerous it becomes. Travelling at even a modest fraction of the speed of light transforms every speck of dust, every stray atom, into a potential catastrophe. This is the problem of impacts, of radiation, of the sheer fragility of matter when confronted with the scales and speeds of interstellar, and especially intergalactic, travel. Let us begin with something simple. Dust. Space is full of it. Tiny particles, most of them smaller than a grain of sand, drift through the void. In the space between stars within our galaxy, there is roughly 1 atom per cubic centimetre. That sounds empty, almost absurdly so. 1 atom in a cube of space the size of a sugar cube. But when you are moving at a significant fraction of the speed of light, even that near-perfect vacuum becomes a problem. At high speeds, collisions with individual atoms release enormous amounts of energy. The faster you go, the worse it gets. This is because kinetic energy, as we have discussed, scales with the square of velocity. When your velocity is measured in tens of thousands or hundreds of thousands of kilometers per second, even a single hydrogen atom carries enough energy to damage your ship. Let us calculate this. Suppose your ship is traveling at 10% of the speed of light, 30,000 kilometers per second. A hydrogen atom, the lightest and most common atom in the universe, has a mass of roughly 1.67 times 10 to the power of negative 27 kilograms. When that atom hits your ship at 10% of light speed, it delivers a kinetic energy of about 7.5 times 10 to the power of negative 14 joules. That does not sound like much. It is a tiny, almost negligible amount of energy. But now imagine you are flying through a region with 1 atom per cubic centimetre, and your ship has a cross-sectional area of, say, 100 square meters. Every second, your ship is sweeping through 3 trillion cubic centimeters of space, colliding with 3 trillion hydrogen atoms. Each one carries that tiny amount of energy, but together they add up to hundreds of watts of continuous bombardment, not devastating, but noticeable. Your ship's hull is being sandblasted by atomic impacts, slowly eroding, heating up. experiencing wear that accumulates over time. Now increase the speed. At 50% of the speed of light, the energy of each collision is 25 times higher. At 90%, it is 81 times higher. The energy scales with the square of the velocity, and as you approach light speed, the impacts become catastrophic. At 99% of light speed, a single hydrogen atom hitting your ship carries the energy of a rifle bullet. A grain of dust, something a millimeter across, hits with the force of an exploding grenade, and space, for all its emptiness, is not perfectly empty. There are regions, especially within galaxies, where the density of gas and dust is higher. Molecular clouds, star-forming regions, the debris of ancient supernovae. Flying through these regions at relativistic speeds would be like flying through a continuous explosion. Your ship would not survive. It would be shredded, vaporized, reduced to plasma in seconds. So any ship traveling at high speeds needs shielding, but shielding against relativistic impacts is extraordinarily difficult. You cannot simply build a thicker hull. The mass of the shielding would add to the mass of the ship, making it harder to accelerate, requiring more fuel, worsening the rocket equation. And no material, no matter how strong, can withstand a continuous barrage of high-energy impacts without eventually failing. One proposed solution is to place a shield ahead of the ship, a sacrificial barrier made of lightweight material that absorbs the impacts. The shield would slowly erode, but the ship behind it would be protected. This could work in theory, but the shield would need to be massive, and it would need to be replaced or replenished regularly. For a journey lasting thousands or millions of years, maintaining such a shield becomes an engineering nightmare. Another solution is to use magnetic fields to deflect charged particles. Many of the atoms in space are ionized, meaning they carry an electric charge, and charged particles can be deflected by magnetic fields. A powerful magnetic shield projected ahead of the ship could push these particles aside, creating a safe corridor through which the ship could travel. This is a more elegant solution, but it requires enormous amounts of energy to generate and maintain the magnetic field, and it does not work for neutral particles like dust grains or neutral atoms, which pass right through magnetic fields unaffected. So even with a magnetic shield, you still need some form of physical barrier to deal with the inevitable neutral matter. But the problem is not just impacts, there is also radiation. Space is flooded with it. Cosmic rays, high-energy particles accelerated by supernovae, pulsars, black holes, and other violent cosmic events zip through space at nearly the speed of light. They are mostly protons, but they carry tremendous energy, far more than the random hydrogen atoms drifting in interstellar space. When cosmic rays hit matter, they create showers of secondary particles, radiation that can damage electronics, degrade materials, and harm living tissue. For a crew traveling through space, especially on a journey lasting decades or centuries, cosmic ray exposure is a serious concern. Without adequate shielding, the cumulative radiation dose could be lethal. Shielding against cosmic rays is difficult because they are so energetic. Traditional shielding materials, like lead, are somewhat effective, but they are also heavy, and adding mass to a spacecraft is always a problem. Lighter materials like water or polyethylene are often better because they contain hydrogen, which is effective at scattering and absorbing high-energy particles. Some ship designs propose using the fuel or water supply as part of the shielding, surrounding the crew compartment with tanks of liquid that serve double duty. This is clever, but it only works as long as you have fuel and water to spare. Once you start using them, the shielding degrades, and for a journey lasting millions of years, even the best shielding will eventually break down. Materials become brittle, structures weaken, the ship itself ages, and there is no port, no repair station, no way to stop and fix things. Then there is the issue of navigation. When you are traveling at high speeds through interstellar or intergalactic space, steering becomes a challenge. At 10% of the speed of light, you are covering 30,000 kilometers every second. There is no time to react to obstacles. If sensors detect a rogue asteroid or a dense patch of gas in your path, you cannot simply swerve. Changing direction at high speeds requires enormous amounts of energy and time. Even a small course correction might take weeks or months to execute, and by then you have already flown past the obstacle or collided with it. So any ship traveling at relativistic speeds needs to map its route carefully before launch, charting a path through the safest regions of space, avoiding known hazards. But space is vast and chaotic. We do not have complete maps. There are objects we cannot see, clouds of gas we have not detected, rogue planets drifting through the dark. Flying blind at high speeds is inherently dangerous, and the faster you go, the less margin for error you have. And this is all just within our galaxy, where the space between stars, though vast, is at least somewhat populated with gas, dust, and the occasional star to navigate by. In intergalactic space, the conditions are even harsher in a different way. The space between galaxies is not like the space between stars. It is emptier, far emptier, with densities so low that you might encounter only a handful of atoms in a cubic meter instead of a cubic centimeter. This sounds like a relief. Fewer impacts, less to worry about. But it also means there is nothing, no stars to use for navigation, no landmarks, just blackness stretching in every direction, broken only by the faint distant glow of galaxies millions or billions of light years away. Navigating through such a void would be like sailing across an ocean with no sun, no stars, no compass, just empty water in every direction. You would have to rely entirely on your instruments, on calculations made before launch, with no way to verify your position until you got close enough to your destination to see it. And if your calculations were off, even by a tiny fraction, you could miss your target entirely, drifting past Andromeda into the endless dark, with no fuel left to correct course. Then consider the psychological toll. A journey through intergalactic space is not a journey past interesting sights or varied landscapes. It is a journey through nothing. For years, decades, centuries, the view outside your ship would be the same. Black, empty, silent. The stars behind you would fade as you moved away. The galaxy ahead would grow slowly, imperceptibly, from a faint smudge to a slightly less faint smudge. There would be no sense of progress, no milestones, no moments of discovery, just the endless, unchanging void. For a human crew, this kind of monotony could be psychologically devastating. Even with artificial environments, with virtual reality, with whatever distractions we could devise, the knowledge that there is nothing outside, that there is nowhere to go, nowhere to stop, no escape, would weigh heavily. This is sensory deprivation on a cosmic scale, and it is not clear that any human mind could endure it for the timeframes required. And if something went wrong, there would be no rescue. No one is coming to help. You are too far away, traveling too fast, moving through a region where no one else is. If a system fails, if the shielding breaks, if the life support malfunctions, the crew would have to fix it themselves with whatever resources they have on board. There is no margin for critical failures. Every component, every system has to work perfectly for the entire duration of the journey, and the longer the journey, the more likely something will go wrong. Entropy is relentless. Things break down, materials fatigue, electronics degrade. No amount of redundancy can eliminate risk entirely. This is why intergalactic travel is not just a matter of building a fast enough ship or finding enough fuel. It is also a matter of survival, of maintaining a fragile bubble of life in an environment that is fundamentally hostile to it. Space does not care about us. It does not accommodate us. And at the speeds necessary to cross intergalactic distances, even the thin wisps of matter that drift through the cosmos become weapons. We are not built for this. Our ships are not built for this. And the universe, indifferent and vast, is not going to change its rules to make it easier. Now we come to one of the strangest and most unsettling barriers to intergalactic travel, one that emerges not from physics or engineering but from biology. We are human. We are made of flesh and bone and neurons. We age. We die. We need air and water and food. We need gravity, or at least something like it, or our bodies begin to break down. We need social contact, purpose, variety. We are fragile in 1,000 ways, and we evolved not for the emptiness of space, but for the surface of a planet, under a sky, surrounded by life. To ask a human body to endure a journey lasting thousands of years, or millions, is to ask something it was never designed to do. And even if we could build the perfect ship, even if we solved every technical challenge, we would still be left with this fundamental problem. We ourselves are the weakest link. Let us start with time. A human lifespan, even in the best conditions, is roughly 100 years. A journey to Andromeda, even at 10% of the speed of light, would take 25 million years. No human could survive that journey, not even close. So the only way to make it work is to involve multiple generations. A generation ship, a vessel large enough to support a self-sustaining population where children are born, live their entire lives, and die aboard the ship, passing the mission on to the next generation and the next for thousands or millions of years. It is a romantic idea, but it is also deeply troubling. Think about what it means. The people who board the ship at launch will never see the destination, nor will their children, nor their grandchildren, nor thousands of generations after them. They are born into a mission they did not choose, living inside a metal container hurtling through the void, with no possibility of leaving, no possibility of turning back. What kind of society could sustain itself under those conditions? What kind of culture, what kind of government, what kind of meaning could hold a community together when the end goal is so distant that it becomes abstract, almost mythical? History shows us that human societies change, languages evolve, beliefs shift. Political systems rise and fall. On Earth, civilizations collapse, knowledge is lost, wars erupt, populations fragment. And that is on a planet with space to spread out, with resources to fight over, with an environment that, however harsh, is familiar. On a generation ship, the constraints are far tighter. The population would be small, perhaps a few thousand people at most, to keep the ship manageable. Such a small population is vulnerable to genetic drift, to the accumulation of harmful mutations, to the loss of diversity. It is also vulnerable to social breakdown. If a faction rebels, if a disease spreads, if a critical disagreement over resources or leadership turns violent, there is nowhere to go. You cannot leave the ship. You cannot call for help. You have to resolve the conflict within the confines of a closed system, or the mission fails. There is also the question of purpose. The original crew, the ones who volunteered and boarded the ship, might have a strong sense of mission. They chose this, they understand the goal, but what about their children and their children's children? They were born into the mission. They had no choice. For them, the ship is not a vehicle. It is the entire world. Earth is not home. It is a story, a myth, something their ancestors left behind so long ago that it has no emotional weight. And the destination, Andromeda, is equally abstract. It is a place they will never see, a goal that exists only in the far future, long after they are dead. Why should they care? Why should they maintain the systems, follow the rules, dedicate their lives to a mission they did not choose and will never complete? It is not hard to imagine a generation ship becoming a society adrift, the original mission forgotten or rejected, the ship itself transforming into a closed, inward-looking world with no connection to its purpose. And then there is the question of what happens when you arrive. Suppose the journey succeeds. Suppose, against all odds, the generation ship makes it to Andromeda, and the descendants of the original crew, thousands or millions of generations later, finally reach their destination. What do? They have spent their entire existence aboard the ship. Their culture, their language, their entire frame of reference is shaped by life in a closed, artificial environment. They know nothing of planets, of weather, of open skies. They might not even think of themselves as explorers anymore. And even if they do, what are they exploring for? By the time they arrive, Earth is gone, or so changed that it might as well be. There is no one to report back to, no one waiting for the data. The mission has become its own end, a journey for the sake of travelling, with no connection to the world that launched it. These are not small problems, they are existential, and they point to a deeper issue. Humans are not interchangeable with machines. We are not logic engines that can be programmed to follow a mission for arbitrary lengths of time. We have needs, desires, fears. We need meaning, we need connection, and we need a sense that what we are doing matters, not in some distant, abstract future, but now, in our own lives. A generation ship asks people to sacrifice not just their own lives, but the lives of countless descendants for a goal that none of them will ever see. It is a kind of multi-generational martyrdom, and it is not clear that any society, no matter how committed, could sustain it. But perhaps we do not need generation ships. Perhaps we could use cryogenic sleep, freezing the crew for the duration of the journey and waking them only when they arrive. This solves the problem of time. A crew in cryogenic sleep does not age, does not consume resources, does not suffer the psychological toll of the journey. They board the ship, they go to sleep, and they wake up at the destination, subjectively experiencing only the moments before and after, as if no time had passed. It is a neat solution, but it is also entirely theoretical. We do not have the technology to freeze a human body and revive it without causing massive tissue damage. Ice crystals form inside cells, rupturing membranes. Metabolic processes stop, but not in a way that can easily be restarted. The brain, the most delicate organ, is especially vulnerable. Freezing it without destroying the intricate network of neurons and synapses is, so far, beyond us. Some researchers are working on vitrification, a process that turns tissues into a glass-like state without forming ice. But even this is experimental and unproven at the scale of a full human body. And even if we solved the technical problem, even if we could reliably freeze and revive people, there is still the question of the ship. Who maintains it while the crew is asleep? Who monitors the systems, makes course corrections, handles unexpected problems? You could automate everything, rely on computers and robots to keep the ship running, but machines break down. Software has bugs. Over timescales of thousands or millions of years, even the most robust systems will fail. You would need either a caretaker crew, people who remain awake and age and die while maintaining the ship, which brings back all the problems of generation ships, or you would need machines sophisticated enough to operate autonomously for the entire journey, fixing themselves, adapting to unforeseen circumstances, making decisions. That is artificial intelligence at a level we do not yet possess, and it raises questions of its own. If the machines are that advanced, why do we need the crew at all? Another possibility is mind uploading, the idea that we could scan a human brain, map every neuron and synapse, and transfer that information into a computer, creating a digital copy of a person that could be run as software. A digital mind does not need air or water or food. It does not age. It does not suffer from radiation or impacts. It could survive the journey in a form immune to the physical hazards of space. And when it arrives, it could be loaded into a new body, biological or robotic, and continue its mission. This is a staple of science fiction, and it might in some distant future become possible. But it is not clear that a digital copy of a mind is the same as the original. If I upload my consciousness into a computer, is that me, or is it a copy that thinks it is me while the original version of me dies? Philosophers have debated this question for decades, and there is no consensus. Even if we set aside the philosophical issues, the technical challenges are staggering. The human brain contains roughly 86 billion neurons, each with thousands of connections. Mapping that structure in enough detail to recreate a functioning mind is beyond anything we can currently do. And even if we could, we do not fully understand how consciousness arises from the physical structure of the brain. We do not know what information is necessary to preserve identity, memory, personality. Uploading is a beautiful dream, but it is far from reality. So we are left with ourselves, with our fragile, aging, biological bodies, and the uncomfortable truth that we are not suited for intergalactic travel. We can imagine workarounds, generation ships, cryogenic sleep, mind uploading, but each one is either unproven, impractical, or laden with problems that might be unsolvable. And this is not even considering the psychological challenges, the isolation, the monotony, the sheer existential weight of traveling through a void so vast that it dwarfs all human experience. We evolved on a planet. We are adapted to gravity, to day and night, to seasons, to the presence of other living things. Take all that away, lock us in a metal box hurtling through the dark for thousands of years, and it is not at all clear that we would remain human in any meaningful sense. We have talked about distance and energy, about time and survival, about the limits of our bodies and our minds, but there is one more aspect of intergalactic space that deserves its own consideration, and it is perhaps the most haunting of all: the voids, the vast empty expanses that lie between galaxies where there is almost nothing, not darkness as we usually imagine it, rich with hidden stars and nebulae, but true emptiness, a kind of cosmic desert so barren that it challenges the very idea of space as something that contains anything at all. These voids are not just obstacles, they are a different kind of space, a different quality of existence, and they represent a boundary that is as much psychological as physical. Within our galaxy, space is full, relatively speaking. There is gas, dust, radiation, magnetic fields. There are stars, planets, comets, asteroids. There is structure. Even in the dark spaces between stars, there is always something nearby, some distant sun you could point to, some nebula glowing faintly, some sense that you are part of a populated universe. But between galaxies, that sense disappears. The density of matter in intergalactic space is so low that it is almost negligible. In the voids between galaxies, you might find one atom in every few cubic meters, compared to one atom per cubic centimeter within a galaxy. That is a difference of 1,000,000 times. It is the difference between a crowded city and an empty wilderness. And the voids themselves, the largest structures in the universe, stretch for hundreds of millions of light years. They are not small pockets of emptiness. They are the dominant feature of the cosmos. Galaxies cluster along the edges of these voids, forming filaments and sheets, while the voids themselves remain almost entirely empty. If you were traveling through one of these voids, the experience would be unlike anything we can easily imagine. Behind you, the galaxy you left, the Milky Way, or perhaps some closer galaxy within our local group, would shrink and fade until it was just a faint smudge of light, one among many scattered across the sky. Ahead of you, your destination galaxy, Andromeda or another, would grow, but so slowly that you could watch for years, decades, centuries, and see almost no change. The light from that distant galaxy would be redshifted, stretched by the expansion of space, dimmed by distance, and in every other direction there would be almost nothing. No stars, no nebulae, no bright objects to break the monotony. Just blackness, deep and absolute, punctuated only by the faint, ghostly glow of distant galaxies, each one an island millions or billions of light years away. This is not the comforting darkness of a night sky on Earth, where the stars feel close, where the Milky Way arcs overhead like a river of light. This is the darkness of true isolation, where the nearest object of any significance is so far away that it might as well not exist, and in that darkness there is no sense of movement. When you travel through a landscape, you see things go by. Trees, mountains, clouds. You have a sense of progress, of covering ground, but in intergalactic space, there is nothing to go by. The distant galaxies do not move. They are so far away that they remain fixed, unchanging, no matter how fast you travel. There are no milestones, no markers, no way to feel that you are getting anywhere. You are moving. You know you are moving because your instruments tell you so, but your senses tell you nothing. You might as well be still. This sensory deprivation is something we have no real experience with. Even astronauts on the International Space Station or on the Moon can look out and see Earth, a vibrant, dynamic, beautiful planet that reminds them of home. They are far from the surface, but they are not alone. They can see life. They can see movement. But in intergalactic space, there is none of that. There is only the ship and the black, and the knowledge that the nearest solid ground is millions of light years away in any direction. For a human mind, evolved to navigate forests and plains, to find comfort in horizons and landmarks, this kind of environment could be profoundly disturbing. It is isolation of a sort we have no evolutionary preparation for, and the voids are not empty in the sense of being peaceful or calm. They are empty in the sense of being absent, of lacking anything that could provide orientation or meaning. There is no sense of scale. No way to tell if you are moving fast or slow, forward or backward, except by trusting your instruments. And instruments can fail, sensors can malfunction, computers can glitch. If you lost your navigation systems, if your instruments stopped working, you would have no way to know where you were going, or even which direction was which. The stars are too dim, too distant, too scattered to use for navigation in the traditional sense. You would be adrift, not in water or air, but in a void so vast that even the concept of being lost becomes inadequate. There is no map that could help you, no rescue that could reach you, just the black and the silence and the slow, inevitable drift. There is also the question of what the voids contain, or rather, what they might contain that we cannot see. Most of the universe is made of dark matter, a substance we have never directly observed but know exists because of its gravitational effects. Dark matter does not emit light, does not interact with electromagnetic radiation in any way we can detect. It is invisible, intangible, but it has mass, and that mass shapes the structure of the universe. Galaxies are embedded in halos of dark matter. Clusters of galaxies are bound together by it, and in the voids there is likely dark matter as well, diffuse and spread out, but present. We do not know what dark matter is. We do not know if it could affect a ship passing through it. Probably not, given that it interacts so weakly with normal matter. But the uncertainty is unsettling. You would be traveling through a medium you cannot see, measure, or understand, with no way to know if it poses a risk. Then there is dark energy, the mysterious force that drives the accelerating expansion of the universe. Dark energy is even more enigmatic than dark matter. It is a kind of pressure, a repulsive force that pushes space itself apart, causing galaxies to recede from each other at ever-increasing speeds. The farther apart two objects are, the faster the space between them expands. Within galaxies, the expansion is negligible, overpowered by the gravitational pull of stars and dark matter holding things together. But in the voids, where there is little mass to counteract it, the expansion of space becomes significant. This has a strange consequence. If you are traveling toward a distant galaxy, and the space between you and that galaxy is expanding, you are fighting against the expansion. You are trying to close a gap that is actively widening. At close range, this is not a problem. Your speed is greater than the rate of expansion, but at very large distances, the expansion can become faster than the speed of light. Not because anything is moving through space faster than light, but because space itself is expanding. And if the expansion is faster than light, then no matter how fast you travel, you can never close the gap. The destination is receding from you faster than you can approach it. This is already true for the most distant galaxies in the observable universe. They are moving away from us so fast, carried by the expansion of space, that we could never reach them, even if we traveled at the speed of light. The light they emitted billions of years ago is only just now reaching us, and the light we emit now will never reach them, because the space between us is growing too quickly. They are beyond our cosmic horizon, unreachable, not because they are too far, but because the universe itself is pulling them away. For galaxies closer to us, like Andromeda, this is not yet a problem. The expansion of space at those distances is slow enough that we could, in principle, overcome it. But over billions of years, the expansion will accelerate. The voids will grow larger. Galaxies that are now reachable will one day be beyond the horizon, and the universe will become a lonelier place. This means that intergalactic travel is not just difficult now, it will become more difficult over time. The window during which such journeys are even theoretically possible is limited. If we wait too long, if we do not act within the next few billion years, the expansion of the universe will make it impossible. The galaxies we could once have reached will drift beyond our grasp, carried away by forces we cannot control into regions of space we can never visit. The universe is not static, it is changing, and the changes are not in our favor. So the voids between galaxies are not just empty, they are expanding, isolating, separating us from everything beyond our local group. And they are vast, incomprehensibly so. To cross one is to commit to a journey through nothingness, through a space that offers no comfort, no landmarks, no sense of progress. It is to become a speck in an ocean of dark, alone in a way that few human minds could endure. And this is not something we can change. We cannot make the void smaller. We cannot fill them with stars or build bridges across them. They are what they are, and they are a wall, not of matter or energy, but of absence, of distance, of the expanding fabric of space itself. And they are why, even if we solved every other problem, even if we built the perfect ship and found the perfect fuel, intergalactic travel would still feel less like a journey and more like an act of desperation, a leap into the dark with no promise of return. By now, we have examined the physical barriers, distance and energy and time, and the biological and psychological ones, the fragility of our bodies, the limits of our minds, the haunting emptiness of the voids. But there is another angle to consider, one that emerges when we ask whether there might be shortcuts, clever ways to bypass the constraints that bind us. Science fiction is full of such ideas, wormholes and warp drives and hyperspace, technologies that let ships hop across vast distances in the blink of an eye, turning the galaxy or even the universe into something manageable, something navigable. These ideas are appealing, and some of them are rooted in real physics. But when we look closely, when we examine what they would actually require, we find that they do not solve the problem. They simply move it somewhere else, into realms so exotic, so speculative, so far beyond anything we can test or build, that they might as well be magic. Let us start with wormholes, one of the most famous shortcuts in theoretical physics. A wormhole is a tunnel through space-time, a shortcut that connects two distant points in the universe. If you could create a wormhole between the Milky Way and Andromeda, you could step through one end and instantly emerge at the other, bypassing the 2.5 million light-years of space in between. No need for relativistic speeds, no need for vast amounts of fuel. Just walk through the door and you are there. It sounds perfect, and the physics, at least in a mathematical sense, allows for wormholes. They are solutions to Einstein's equations of general relativity, valid configurations of space-time that could, in principle, exist. But there are problems, enormous problems. First, wormholes are not stable. The equations that describe them show that they collapse almost as soon as they form, pinching off and severing the connection between the two ends. To keep a wormhole open, to stop it from collapsing, you would need something called exotic matter, a substance with negative energy density. This is not ordinary matter. It is not antimatter, which has positive energy. Exotic matter is something far stranger, something that pushes instead of pulls, that repels gravity instead of attracting it. We have never observed exotic matter in nature. We do not know if it can exist in the quantities required. Some physicists speculate that quantum effects might allow for small amounts of exotic matter under very specific conditions, but the amounts needed to stabilize a wormhole large enough for a spacecraft or even a person to pass through would be staggering. We are talking about negative energy equivalent to the mass of a star or a galaxy or more. Even if exotic matter exists, gathering enough of it, controlling it, shaping it into a configuration that holds a wormhole open is so far beyond our capabilities that it is hard to take seriously as a practical solution. Second, even if we could stabilize a wormhole, we would have to create it in the first place. Wormholes do not occur naturally, as far as we know. They are not features of the universe we can discover and use. They would have to be built, engineered from scratch, using technologies that do not exist and may never exist. Some theories suggest that microscopic wormholes might have formed in the early universe during the Big Bang, but these would be far too small to be useful, and they would have collapsed long ago. To create a macroscopic wormhole, one large enough for human travel, would require manipulating space-time on scales and with precision that dwarf anything we have ever done. It would be, in a very literal sense, remaking the fabric of reality. And even if we did it once, creating a wormhole between 2 points, we would have to physically carry one end of the wormhole to the destination, moving it through normal space. That means the first trip still has to be done the slow way, the hard way, traveling through intergalactic space at whatever speed we can manage, carrying the wormhole mouth with us. Only after that journey is complete could we use the wormhole for instant travel, so wormholes do not eliminate the need for intergalactic travel. They just allow us to do it once, painfully, and then make subsequent trips easier. And that is assuming the physics even works, which is a very big assumption. Then there is the warp drive, another staple of science fiction. The idea here is to distort space-time around a ship, contracting the space in front and expanding the space behind, so that the ship rides a wave of space-time toward its destination. The ship itself does not move through space at faster than light speeds. Instead, space moves around the ship. This is a clever way to sidestep the light speed limit, which only applies to objects moving through space, not to the motion of space itself. Warp drives are also rooted in real physics. The Alcubierre drive, proposed by physicist Miguel Alcubierre in the 1990s, is a mathematical model showing that such a configuration of spacetime is, in principle, possible, but like wormholes, it comes with insurmountable problems. The first problem is energy. Creating a warp bubble requires enormous amounts of negative energy, just like stabilizing a wormhole. Early estimates suggested the energy equivalent of the mass of Jupiter converted entirely into exotic matter. Later refinements brought the number down, but even the most optimistic estimates still require negative energy on a scale we cannot produce. We are not talking about a lot of fuel. We are talking about warping space-time itself, bending the structure of reality into an unnatural shape, and holding it there while the ship travels. This is not something you can do with a fusion reactor or even antimatter. It requires something we do not have and cannot make. Second, there is the problem of causality. If you can travel faster than light, even by warping space, you can, under certain conditions, travel backward in time. This is a consequence of special relativity. Faster-than-light travel opens the door to time travel, and time travel opens the door to paradoxes, situations where you could, in theory, arrive before you left, or change the past in ways that prevent your own departure. Physics does not like paradoxes. They suggest that something is wrong with the theory or the setup. Most physicists believe that the universe has some mechanism, something we do not yet understand, that prevents such paradoxes from occurring. This might mean that warp drives, even if we could build them, simply would not work in the way we expect. The universe might have rules deeper than the ones we know that forbid faster-than-light travel in any form. Then there is hyperspace, the idea that there is another dimension, a different layer of reality, where the normal rules of space and distance do not apply. Ships could enter hyperspace, travel quickly through this alternate realm, and then emerge back in normal space at a distant location. This is pure speculation. There is no evidence for hyperspace. No theory in physics predicts it. It is a narrative device, useful in stories, but disconnected from anything we can measure or test. Could there be extra dimensions? Yes. String theory suggests there might be 10 or 11 dimensions, most of them curled up so small that we cannot perceive them. But these extra dimensions are not shortcuts. They are not places you can go. They are part of the structure of space at the smallest scales, and they do not provide a way to bypass the vast distances of the universe. There is also the possibility of using black holes or other exotic objects as gateways. Some theories suggest that rotating black holes, Kerr black holes, might contain pathways through space-time, allowing travel to distant regions or even other universes. But the problem is survival. The tidal forces near a black hole, the difference in gravitational pull between your head and your feet, would tear you apart long before you could pass through any hypothetical gateway. And even if you could survive, we have no idea where such a pathway would lead. It might take you to another part of our universe, or it might take you somewhere else entirely, somewhere you could never return from. Black holes are not tools we can use, they are hazards, regions of space-time so warped and extreme that nothing, not even light, can escape once it crosses the event horizon. All of these ideas, wormholes, warp drives, hyperspace, black hole gateways, share a common problem. They rely on physics we do not understand, phenomena we have never observed, technologies we cannot build. They are mathematically interesting, and they make for compelling stories, but they are not solutions. They are speculations, hopes, dreams dressed up in equations. And even if they were real, even if we discovered tomorrow that wormholes can be stabilized or warp drives can be built, the challenges would still be immense. The energy requirements, the engineering, the risks, all of it would still be staggering. These shortcuts do not eliminate the barriers. They just replace them with different, equally insurmountable barriers. And there is a deeper issue. Even if we could use these exotic technologies to reach other galaxies, what would we find? Another galaxy full of stars and planets. Sure, but why go? What is the purpose? If the goal is exploration, we have billions of stars in our own galaxy to explore, most of them far closer and far more accessible than anything in Andromeda. If the goal is colonization, to spread humanity across the cosmos, we have an entire galaxy to fill. It would take millions of years to colonize even a fraction of the Milky Way, assuming we ever develop the means. By the time we exhaust the possibilities within our galaxy, if that ever happens, we will have changed so much, evolved so much, that we might not even recognize ourselves. The civilization that sets out to colonize other galaxies, if it ever exists, will not be us. It will be something descended from us, something adapted to space, to time, to scales of existence we cannot currently imagine. And they might look at intergalactic travel and decide it is still not worth it, that the galaxy they have is enough. So the shortcuts do not save us. They are beautiful ideas, intellectually fascinating, but they are not practical. They do not overcome the fundamental limits imposed by physics. And even if they did, they would not change the fact that we are small, fragile, and bound by the structure of space-time itself. The universe has rules, and those rules are not flexible. They are not suggestions. They are the framework within which everything, including us, exists. And within that framework, intergalactic travel remains out of reach, not just technologically, but perhaps conceptually. It is not the kind of thing biological beings can do, and it might not be the kind of thing the universe allows at all. Now we turn to a different kind of question, one that steps back from the mechanics and the math and asks what it all means. If we are trapped here, if intergalactic travel is impossible or so impractical that it might as well be impossible, what does that say about us, about our place in the universe, about the chances of ever meeting another civilization? Because we are not the only ones bound by these limits. Every intelligent species everywhere faces the same walls we do, the same speed limit, the same energy barriers, the same voids. And if those barriers are truly insurmountable, if no one can leave their galaxy, then the universe is not a connected place. It is a collection of isolated islands, each one home to civilizations that will never meet, never communicate, never know that the others exist. This is the Fermi paradox from a different angle, and it is both humbling and strangely comforting. The Fermi paradox, named after physicist Enrico Fermi, is the question of why, if the universe is so large and so old, we have not seen any evidence of extraterrestrial civilizations. The numbers suggest we should have. There are hundreds of billions of stars in our galaxy alone, many of them with planets, some of those planets likely habitable. Even if life is rare, even if intelligence is rarer still, the sheer scale suggests there should be others out there. And if even a small fraction of those civilizations developed technology, if even a few reach the stage where they could build ships and travel between stars, we should see signs of them. Megastructures, radio signals, probes, something. But we see nothing. The sky is silent. We are alone, or we appear to be, and that silence is one of the great mysteries of our time. There are many proposed solutions to the Fermi paradox. Maybe life is much rarer than we think. Maybe intelligence is a fluke, a one-time accident that happened here and nowhere else. Maybe civilizations tend to destroy themselves before they can spread, wiped out by war or environmental collapse or some other self-inflicted catastrophe. Maybe they are out there, but they are hiding, staying quiet for reasons we do not understand. Or maybe space is just too big, the distance is too vast, and the chances of two civilizations overlapping in time and space are vanishingly small. Each of these explanations has its own problems and its own appeal. But there is another possibility, one that fits with everything we have discussed. Maybe civilizations do not spread across galaxies because they cannot. Maybe the barriers are real, and no one, no matter how advanced, can overcome them. This does not mean that space travel is impossible. We have already sent probes beyond the solar system. We could, in principle, build ships capable of traveling to nearby stars within our galaxy if we were willing to accept journey times of centuries or millennia. The stars are far, but they are not impossibly far. A sufficiently motivated civilization with enough resources and a long-term perspective could colonize its galaxy over millions of years. Slowly, patiently, spreading from star to star, never moving faster than a few % of light speed, but covering ground through persistence. In time, such a civilization could fill its galaxy, or at least a significant portion of it. But filling a galaxy takes time. Millions of years, tens of millions, and during that time the civilization itself will change. Evolution will not stop, technology will advance, culture will shift. By the time a civilization has spread across its galaxy, it will have fragmented into countless subgroups, each one adapted to its own environment, each one following its own path. The original unity, the shared identity that started the expansion, will be lost. What remains will be a network of related but distinct societies, each one as different from the others as we are from our distant ancestors. And even if a civilization fills its galaxy, even if it masters interstellar travel to the point where moving between stars becomes routine, it still faces the same barrier when it looks outward to other galaxies. The distances do not shrink, the energy costs do not drop, the voids do not become less empty. Intergalactic travel remains just as impossible for an advanced civilization as it is for us, because the limits are not technological, they are physical, they are built into the structure of space-time. A civilization that can travel between stars is still bound by the speed of light. It still needs energy. It still faces the problem of time dilation, of survival, of crossing voids where there is nothing. The barriers do not go away just because you are more advanced. They are universal, and they apply to everyone. This suggests a picture of the universe very different from the one we see in science fiction. Not a bustling, interconnected network of civilizations trading ideas and resources across the stars, but a quiet, fragmented cosmos where each galaxy is its own isolated bubble. Within a galaxy, there might be civilizations, there might be empires, federations, networks of inhabited worlds. But each galaxy is separate. Each one is its own universe, in a practical sense, because the space between galaxies is uncrossable. Civilizations in Andromeda will never meet civilizations in the Milky Way. They will never know we are here, and we will never know they are there. We are neighbors in space, but we are separated by a gulf so vast that it might as well be infinite. This has implications for how we think about our future. If intergalactic travel is impossible, then our long-term destiny, if we survive, is tied to our galaxy. The Milky Way is our home, not just now, but forever. Everything we will ever do, every world we will ever inhabit, every civilization we will ever build, will be contained within this one structure. The galaxy is large, unimaginably so, and it offers more than enough space for any future we can conceive. But it is also a boundary. We will never leave it. We will never see what lies beyond except as distant points of light, forever out of reach. And this might explain the silence. If every civilization is trapped in its own galaxy, then the Fermi paradox is less paradoxical. We do not see other civilizations because they are not here. They cannot be here. They are in their own galaxies, facing their own challenges, building their own futures, just as isolated as we are. The universe is not empty. It is probably teeming with life, scattered across billions of galaxies. But each instance of life is alone, cut off from the others by distances that cannot be bridged. We are all islands, and the ocean between us is too wide to cross. This is both a sobering and a liberating thought. Sobering because it means we will never meet our cosmic neighbours, never share our stories or learn from theirs. We will never see the wonders they have built or understand the paths they have taken. We are alone in a way that is absolute, not because there is no one else out there, but because the universe has made it impossible for us to reach them. But it is also liberating because it means we are free. We do not have to compete with other civilizations. We do not have to fear invasion or conquest from beyond. The galaxy is ours if we choose to take it, and no one is coming to take it from us. Our future is our own to shape, constrained only by our choices and our limits, not by the ambitions of others. It also suggests a kind of humility. We are not the center of anything. We are not special or unique in the grand scheme. Somewhere in a galaxy far away, another species is having the same realization, looking up at their sky, wondering if they are alone, and coming to the conclusion that they are trapped just as we are. And they will build their civilizations, and they will thrive or fail, and they will leave their mark on their corner of the universe, and we will never know, just as they will never know about us. The cosmos is full of stories, billions of them, each one unfolding in isolation, each one significant to those who live it, each one invisible to everyone else. We are one story among many, and our isolation is not a flaw. It is simply the way the universe is. As we near the end of this journey through the barriers that confine us, it is worth pausing to consider what we have learned, not just about the impossibility of intergalactic travel, but about the nature of limits themselves. We live in an age that celebrates progress, that assumes every problem has a solution, that believes technology and determination can overcome any obstacle. And in many cases, that belief has been justified. We have split the atom, decoded the genome, walked on the moon. We have connected the entire planet through a web of communication, and we have built machines that think, that learn, that see and hear and respond. It is tempting to believe that there is no limit to what we can do, that every horizon is temporary, waiting to be crossed. But the universe does not care about our ambitions. It does not adjust its rules to accommodate our dreams. And some limits, the ones we have explored here, are not challenges to overcome. They are boundaries, written into the structure of reality itself. They are not temporary, they are not technological, they are fundamental, and recognizing them, accepting them, is not defeat. It is wisdom. It is understanding that we are part of a cosmos far larger and older than we are, a cosmos that existed long before us and will continue long after we are gone. And within that cosmos, there are places we cannot go, things we cannot do, mysteries we cannot solve. This does not mean we should stop trying. Within our galaxy, there is more to explore than we could ever exhaust. There are hundreds of billions of stars, many of them with planets, some of those planets perhaps harboring life. There are nebulae and black holes and neutron stars, objects so strange and extreme that they challenge our understanding of physics. There are worlds waiting to be discovered, civilizations that might have risen and fallen in the deep past, leaving traces we have not yet found. The Milky Way is our frontier, and it is vast beyond comprehension. We could spend millions of years exploring it and still not see everything. And if we are clever, if we are persistent, if we survive the challenges ahead, we might one day spread across the galaxy, building homes on distant worlds, creating new societies, new cultures, new ways of being human. That future is possible, difficult, but possible, and it is more than enough. But intergalactic travel is different. It is not just difficult. It is not just beyond our current technology. It is beyond any technology we can imagine, because it is not a technological problem. It is a physics problem, and the physics says no. Distance, energy, time, survival, the voids, the expansion of space itself, all of them point in the same direction. We will not leave our galaxy, not us, not our descendants, not any future civilization that arises from our lineage. The Milky Way is our home, and it will remain our home forever. That is not pessimism, it is reality. And there is a kind of peace in accepting it, in letting go of the dream of infinite expansion and embracing the enormity of what we already have. There is also a lesson here about the limits of knowledge. We know a lot about the universe. We have measured its age, mapped its structure, uncovered the laws that govern its behavior. We have peered back to the earliest moments after the Big Bang and forward to the eventual heat death of the cosmos. We understand in broad strokes how stars are born and how they die, how galaxies form and how they evolve, but there is still so much we do not know. Dark matter, dark energy, the nature of quantum gravity, the possibility of other universes, these are open questions, and they might remain open for a long time, perhaps forever. The universe does not owe us answers. It does not guarantee that every mystery can be solved. And some of the things we do not know might be unknowable, not because we are not smart enough, but because the information is not accessible, or because the questions themselves are not well formed. Intergalactic travel sits at the edge of this boundary. It is not quite unknowable. We can understand why it is impossible. We can trace the limits back to first principles, to the speed of light, to the nature of space-time, to the rocket equation. But knowing why something is impossible does not make it less frustrating. We want to explore. We want to push boundaries. We want to know what is out there, and the universe, indifferent and vast, tells us that some boundaries cannot be pushed, that some places are simply beyond our reach. And yet, there is something profound in that limitation. It binds us to our home, to the Milky Way, to the star system we were born in. It forces us to reckon with the fact that we are not the conquerors of the cosmos, but its inhabitants, subject to its rules, shaped by its forces. We are part of the universe, not separate from it, and the limits that bind us are the same limits that define everything else. Stars cannot escape their gravity. Light cannot exceed its speed. Black holes cannot release what they have swallowed. Everything is constrained, everything is limited, and those limits are not failures. They are the structure that makes the universe intelligible, that gives it order and predictability. Without limits, there would be chaos. Without constraints, there would be no form, no meaning, no stories to tell. So we are trapped in our galaxy, but it is a beautiful trap. The Milky Way is ancient and vast and filled with wonders we have barely begun to glimpse. It is a spiral of light, a disk of stars rotating slowly around a supermassive black hole, its arms traced out in gas and dust and the birth of new suns. It is our cradle, and it might one day be our empire, if we are wise enough, patient enough, brave enough to take on the challenge. And if we never leave, if we spend the rest of our existence confined to this one galaxy, it will still be more than enough. More than we can explore in 1,000,000 lifetimes, more than we can understand in 1,000 generations. So let us not mourn what we cannot do. Let us celebrate what we can. Let us look outward, not with the expectation of crossing every distance, but with wonder at the sheer scale and beauty of the cosmos. Let us recognize that we are small, yes, but also part of something immeasurably large. And let us accept that some horizons are meant to be admired, not crossed, that some mysteries are meant to remain mysteries, and that our place in the universe, finite and bounded as it is still extraordinary. And so we arrive at the end of this long journey through the barriers that define our cosmic home. We have travelled far tonight, not through space, but through ideas, through the mathematics and physics that govern reality, through the implications of distance and time and energy, through the voids and the silence and the limits that no amount of ingenuity can overcome. And we have arrived at a conclusion that is both humbling and, in its own way, strangely comforting. We will not leave our galaxy. The Milky Way is not just our current home. It is our permanent one, our only one, the stage on which the entire human story, and perhaps the story of all life that arises from Earth, will unfold. This is not the ending we might have hoped for. It is not the triumphant narrative of humanity spreading across the cosmos, planting flags on the shores of distant galaxies, building empires that span the universe. But it is the truth, or as close to the truth as our current understanding allows. And there is value in truth, even when it is not what we wanted to hear, because truth anchors us. It gives us a foundation. It tells us where we stand and what is possible. And from that foundation, we can build something real, something lasting. The galaxy is ours if we survive long enough to claim it. It is vast beyond imagination, filled with stars and worlds and possibilities we have not yet dreamed of. And if we are careful, if we learn to live sustainably, if we overcome the challenges that currently threaten us, climate change and conflict and the fragility of our ecosystems, we might one day look back on this moment as the beginning of something extraordinary. Not the conquest of the universe, but the maturation of a species, the moment when we stopped dreaming of infinite expansion and started building a future within the boundaries that actually exist. There is a certain beauty in limits. They force us to focus. They force us to make choices. If we knew we could go anywhere, do anything, the galaxy might seem less precious. But knowing that this is all we have, that the Milky Way is the sum total of our possible future, gives it weight. It makes every star in our galaxy matter. It makes the search for life within our own cosmic neighborhood more urgent, more meaningful. If there are others out there, other civilizations in the Milky Way, they are the only neighbors we will ever have. We are bound together, not by proximity in the usual sense, but by the fact that we share the same island, the same isolated bubble of stars. And if we ever do make contact, if we ever find a signal from another world, it will not be from a distant galaxy. It will be from here, from our galaxy, from a fellow traveler in the same small corner of the universe. And if we never find anyone else, if we are alone in the Milky Way, that too has meaning. It means we are the only voice in this part of the cosmos. The only ones asking questions, seeking answers, creating art, building civilizations. It means the galaxy is silent, waiting, and we are the ones who can fill it with sound and light and life. That is not a small thing. That is not a disappointment. That is a responsibility and a privilege. So perhaps the question is not why we cannot leave the galaxy, but why we would want to. What are we searching for out there, beyond the edge, that we cannot find here? Knowledge. There is more knowledge within the Milky Way than we could gather in 1 billion years. Beauty. The galaxy is full of it, nebulae glowing in shades of red and blue, star clusters sparkling like diamonds, planets with rings and moons and storms that rage for centuries. Connection. If there is anyone to connect with, they are here, not in Andromeda. Purpose? We make our own purpose. We define what matters. And we can do that just as well, perhaps better, within the bounds of our own galaxy, as we could in some imagined universe where all distances are bridged and all galaxies are open. There is also something to be said for the idea of home. We spend so much time looking outward, imagining what lies beyond the next horizon, that we forget to appreciate where we are. Earth is our home, the solar system is our home, and the Milky Way, vast and ancient and full of mystery, is our home. We are part of it. We are made of its matter, carbon and oxygen and iron forged in the hearts of its stars and scattered into space when those stars died. We are, in a very literal sense, stardust, the universe looking back at itself. And the galaxy that made us is the galaxy that will hold us. We are bound to it, not by chains, but by the simple fact that this is where we belong. And there is a kind of poetry in that, in all the vastness of the cosmos, in all the billions of galaxies scattered across space. We have this one, this spiral of light, this disk of stars, this home. And it is enough. It has to be enough, because it is all we will ever have. But enough is not the same as insufficient. Enough can be abundant. Enough can be overwhelming. The Milky Way is not a cage. It is a garden, vast and strange and full of places we have never seen. And we are the gardeners if we choose to be. We are the ones who can explore it, understand it, protect it, fill it with life and meaning. So let us not mourn the galaxies we will never visit. Let us not spend our nights staring at Andromeda with longing and frustration. Let us instead turn our gaze to the stars that are ours, the ones we can reach, the ones that might, someday, be home to our descendants. Let us celebrate the scale of what is possible, even within limits. Let us recognize that a single galaxy is more than enough for any species, more than enough for 1 million species, more than enough for stories and dreams and futures beyond counting. And when we look up at the night sky, when we see the faint band of the Milky Way stretching overhead, let us remember that we are looking at our home, not the blue marble we walk on, but the larger home, the structure of stars and gas and dark matter that holds our solar system, that gave birth to our sun, that will endure long after we are gone. We are part of it, and it is part of us. And the bond between us is unbreakable, not because we lack the technology to leave, but because leaving was never the point. The point was always here. It was always about understanding where we are, who we are, what we can become, and the answers to those questions do not lie in distant galaxies, unreachable and silent. They lie here, in the stars around us, in the planets we have yet to explore, in the life we have yet to find, in the civilizations we have yet to build. The Milky Way is not a limit. It is a horizon, wide and endless, full of possibilities we cannot yet imagine, and that is more than enough. So rest now, let your mind settle, let the weight of these vast distances, these impossible barriers, these unbreakable limits sink in, not as a source of despair, but as a kind of grounding. We are here, we are home, and the galaxy that holds us is ancient and beautiful and full of light. We will never leave it, and that is okay, because within it, there is more than we could ever need, more than we could ever explore, more than we could ever understand. Sleep well, traveller. The stars are still there, waiting, close enough to dream about, far enough to remain mysterious. And in the morning, when you wake, you will still be here in this galaxy, on this world, part of this vast and ancient structure. And that is exactly where you are meant to be,